Thank you. Yeah, thank you for the introduction and the invitation to speak. I'll be talking about the joint work in progress with Max Kaipel, Klapproth and K Schlegel, where we study brick-finiteness under base field extensions. And this behavior is pretty bizarre because it's very different from representation-finiteness under base field extensions, as we'll see pretty soon. First, I will recall the definitions and then show you that a classical result fails to hold when generalizing from rep-finiteness to brick-finiteness. So, definitions. I will fix a field, K, and a finite-dimensional algebra lambda over K. In this setting, a finally generated right module B over lambda is called a brick if its endomorphism algebra, N of B, is the division algebra over K. And also, lambda will be brick finite if it only admits finitely many bricks up to isomorphism. If that's not the case, it is brick infinite. I will state some remarks that will be useful later. Firstly, any rep-finite algebra is brick finite. Basically, immediately from the definition, because the division algebra is local, so any brick will be indecomposable, more or less by definition. However, you can find rep-infinite algebras that are brick finite, because any local k-algebra is brick finite, and there are rep-infinite local k-algebras. So this is a strict generalization of rep-finiteness, brick-finiteness, that is. If you want an example of brick-infinite algebra, look no further than the Kronecker algebra, because every single indecomposable pre-projective module is going to be a brick, and there are infinitely many of those. So that's a known example of a brick-finite algebra. Finally, brick-finiteness is preserved under algebra quotients, because if I have an ideal I of lambda, then the module category of lambda modulo I embeds fully faithfully into the module category of lambda, and that induces an injection from bricks up to isomorphism over lambda modulo I to bricks up to isomorphism over lambda. So please keep these four remarks in mind for two more slides, because they'll be useful in a proof sketch a little bit ahead. I will now extend the setting slightly by extending my base field. So I will fix L to be a field extension of K, and then define the extension of scalars, which is now a finite-dimensional L-algebra given by tensoring the k-algebra lambda with L over K. Now, for our purposes, some field extensions are nicer than others, and by nice, I will usually mean MacLane separable. On this occasion, in this very short talk, I have no time to define MacLane separable extensions. They go back to MacLane, and they were immortalized by Key. But I will say that any separable extension is MacLane separable, and it's a rather mild generalization of separable extensions, because if the extension L over K is algebraic, then it is MacLane separable if and only if it is separable. We are ready to state a classical result due to Jensen and Lenzing from 1982, which is that MacLane separability is enough to guarantee that rep-finiteness is preserved for algebras. So if L over K is MacLane separable, as stated here, and lambda is rep-finite, then the extension of scalars lambda L is also rep-finite. That will be this implication, and the reverse implication is always true. So left to right is more interesting, and can only be guaranteed to hold if L over K is MacLane separable. So now this begs the question: can we replace the word rep-finite here and here with brick-finite? Is brick-finiteness preserved under MacLane separable field extensions? The answer turns out to be no, and it's a very resounding no. It is somehow bizarrely seems to flip, actually. And I will show you an easy example of this, which can be extended to a general result. So the proposition here is now joint work in progress with my three co-authors, and a version of the example we see in this proof sketch appears in the preprint of Max Kaipel on the archive. The thing is, we observe this, Max and I, that it fails to hold for the real and complex numbers. And then using the same ideas, we extended it more broadly with Carlo and Kevin. My conclusion will be that if L over K is non-trivial, separable, and algebraic, then I'm able to construct an algebra, lambda over K, which is brick finite, but is such that lambda L is brick infinite. It's actually even worse. If you only have an element alpha in L but not in K, which is algebraic and separable over K, then you can construct this algebra lambda, which is brick finite, for which lambda L is brick infinite. So I'll go through this example. So if I have the simple or very easy extension C over R, then this algebra here can be shown to be a local algebra, and thus it is brick finite. However, if you tensor this algebra with C, giving you C algebra, it will be isomorphic to this bound path algebra. But this bound path algebra, you can see, has the Kronecker algebra as a quotient. So this one cannot, lambda C cannot be brick finite. That would imply that the Kronecker algebra B would be brick finite, which it is not. So using similar ideas, and somehow the generalization is not immediate, but there are no surprises when generalizing from this to general case. You can use this element alpha to construct this algebra lambda, showing this thing proposition here holds in more generality than the example shown in this proof sketch. All right. I will say that we have more results coming up. We are approaching results showing that somehow uglier field extensions behave better under scalar extension. I'm not ready to state them now, but I will say that they will appear in future talks by myself and my co-authors.